Hi, welcome to the second part of the lecture on Turing reductions. And today we'll also learn about a new topic, which is the hierarchy of undecidability. So to briefly recall, in previous class, we started off by defining this really beautiful notion of Oracle Turing machines, which generalizes the multi-tape Turing machine model that you have learned before. And then we defined what it means for a language to be Turing reducible to a different language. We saw a couple of examples of familiar languages that you have seen and how they're, Turing reducible among each other. And today's lecture is more going to focus on its implication. So let's start off with that. So the first important theorem that we are going to prove, it's relatively straightforward to prove, but it's really the implication of, Turing reducing one language to other, which is if a language A is Turing reducible to B and B is decidable, then A is decidable. All right. So this is kind of the main power of Turing reducing language A to B. That we could state it contrapositively stated. Contrapositively, it means that if A is Turing reducible to B, and we know that A is undecidable, then B is also undecidable. All right. So if you're trying to prove, so suppose you're given a language B and you're trying to prove that it's undecidable, then pick the favorite problem that you have that that is undecidable and show a Turing reduction from that language to the target language B, and that will prove that B is undecidable. Okay, so let's actually try to prove this theorem. It's relatively straightforward. So I'll just try to sketch the proof. And the proof sketch is essentially just the intuition that you have that so we are trying to prove that A is decidable, knowing that B is decidable. So suppose suppose MB decides A. Well, we do know that from just the definition of Turing reducibility, that since A is Turing reducible to B, it must be that, there is an Oracle Turing machine with Oracle access to B that decides A, right? Now, for every Oracle call to B, you replace it with computation of the decider for B. All right, so given this Oracle Turing machine, now let's try to construct a new Turing machine, which is just a simple plain Turing machine without any Oracle access, which does the following: that whenever it tries to simulate this Oracle Turing machine, and whenever this Oracle Turing machine does an Oracle query, it just replaces that query with actually simulating computation of the decider for B, right? And why do you have a decider for B? It's, it's from this assumption that B is decidable. So there's a Turing machine which decides B. And in this way, you can, replace each Oracle call with computation of the decider to get, the answer to your Oracle query. And hence what you end up with is just a normal Turing machine which decides A, and this completes the proof sketch that given an Oracle Turing machine for A, you can actually convert it into a regular Turing machine for A. All right. So, for instance, in the previous lecture, we proved that ETM is Turing reducible to halt TM, right? So using this, what can we infer? We can infer that undecidability of ETM implies undecidability of halt TM, right? So suppose you know that ETM is undecidable, you have the Turing reduction from ETM to halt TM, it would imply the undecidability of halt TM. All right, and also an important observation is that such a theorem does not hold for recognizability. So it is not true. So not true. What is not true? That if A is Turing reducible to B and B is recognizable, then A is recognizable. So again, emphasis on it's not true. And what's a simple counterexample for this? Well, we already saw a counterexample in the previous class, which is, so what's the counter example? Well, you can take A to be ATM, complement, and B to be ATM. Well, we do know, as we saw in the previous class, that it's really simple to come up with a Turing reduction from ATM complement to ATM. But note that, this is recognizable, but this is not Turing recognizable. So this is unrecognizable. And this provides the necessary counterexample that you need to, see that it does not hold that, such a theorem's version does not hold for recognizable languages. Okay. All right. So that's kind of the key use of Turing reductions to prove undecidability of languages. And related to this, I mean, as you saw, we defined Turing reductions via Oracle Turing machines. And a very natural question to ask is the following. So the natural question to ask is, how powerful are Oracle Turing machines, right? Of course, one could say that, the power depends on which Oracle you have access to. But in a generic way, suppose, can we say anything about, the power of an Oracle Turing machine, irrespective of how, powerful or expressive the Oracle is. And here is something which is pretty astonishing. But also, if you think a bit deeper, maybe it's kind of expected that for any Oracle B, there are languages that cannot be decided by any Turing machine with Oracle access to B. All right. And this kind of gives way to this hierarchy of undecidability that no matter how powerful the Oracle you have, there are languages out there which are beyond the scope of being decided by Turing machines with Oracle access to B. All right. And this is going to be the rest of this lecture. We'll actually, show examples of languages which are beyond scope of Turing machines with powerful oracles. So let's actually try to make this more precise. Let's make this more precise. All right, so define halt Tm prime to be mx such that m halts on x with Oracle access to halt Tm. All right, so this is kind of a generalization of the halting problem that you have seen, which is now we are reasoning about Oracle Turing machines. So M is an Oracle Turing machine which actually has Oracle access to halt Tm. And now you accept all tuples M comma X such that M halts on X, having access to halt Tm. And here is kind of the claim which says that, even powerful oracles are not useful sometimes. And the claim is that halt Tm prime cannot be decided by any Turing machine with Oracle access to halt Tm. All right, so it shows a specific language, halt Tm prime, which is beyond the scope of being decided by any Turing machine which has access to a powerful Oracle. It has access to halt Tm, which by itself is an undecidable language, right? All right, so let's actually try to prove this claim. It's a pretty powerful claim, right? So, Turing machines with powerful oracles also cannot decide some languages. Okay, and the proof is actually pretty similar to the way you proved, that the halting problem is undecidable. It uses diagonalization in a way that you have seen before. So it's similar to prove that halt Tm is undecidable and uses the technique of diagonalization. Okay, so let's actually go through the proof. Okay, so suppose for sake of contradiction that, Turing machine H with Oracle access to halt Tm decides halt Tm prime, right? So suppose, you have an Oracle Turing machine with access to the Oracle halt Tm and actually can decide halt Tm prime. Using this, let's consider a different different machine, consider a different Oracle Turing machine which also has access to halt TM, that on input X does the following. So let MX be the Turing machine represented by X. So X is the string which is code for the Turing machine MX. So on input X, what T does is it simulates the machine H, which we assumed, is the decider for halt TM prime. So it simulates H on input MX, X. All right. And note that, this simulation is actually possible, right? This simulation is possible since T has Oracle access to halt TM. Right? So whenever, H makes an Oracle query to halt TM, T can do a similar query and, get the simulation through. And then it just does the usual trick of diagonalization, which is if H halt TM accepts the pair MX, X, then T halt goes into an infinite loop, and else, so let's number this 3. So else meaning if H halt actually rejects the input MX, X, then T halt accepts the input X. All right. So this is the entire description of T halt. So it's the usual diagonalization trick, which is kind of trying to contradict the working of H halt. And now to get the final contradiction, we do the following, which is what is the behavior of T halt on input T halt, so the code of T halt. So it's the string which corresponds to the code of T halt. And we'll show that any behavior is a contradiction, which will end up contradicting the existence of H halt. Okay, so for starters, suppose, that TH halt accepts the code to itself. So if TH halt accepts the input, what it means is that we are in this case, right? That's the only way T halt accepts an input. And in that case, it must be that H halt TM rejects the input T halt and the code to T halt, right? And if this is the case, well, if H halt rejects this, it means that T halt does not halt on the input t halt, the code to t halt. And this is a contradiction, right? Because we, started out with the assumption that, t halt accepts the input, the code to t halt, but now we arrived at the conclusion that it does not halt in this input, which is a contradiction. And the other case is also pretty similar. So suppose, so suppose t halt of tm does not accept the input, which is the code to itself. In this case, the claim is that, the only way t halt does not accept anything is if it's in this case, which is, t halt goes into an infinite loop. So what are the observations? So one is t halt goes into infinite loop, and also the fact that, we are in this case, which means that h of halt tm actually accepts the input, which is t halt and the code to t halt, right? And h halt accepting this means that, t halt halts sorry, it should have a few tms here. T halt of tm halts on the code t halt of tm, and 1, 2 contradict each other. All right. So in either case, we see that we arrive at a contradiction, which means that h halt cannot exist. And this completes the proof that, indeed, it's not possible to decide the language halt tm prime using any Turing machine which has Oracle access to halt tm. Okay, and the final concluding remark of today's lecture is that, okay, so we have shown that, there are languages out there that cannot be decided by Turing machines, which has access to halt tm, which has Oracle access to halt tm, and one can, continue in the same way, right? So similarly, one can show halt tm double prime, which is mw such that m halts on w with Oracle access to halt tm prime now is undecidable by Turing machines with Oracle access to halt tm prime. All right, so the proof is again similar, and one can generalize this to define halt tm triple prime, which has Oracle access to halt tm double prime now, and so on. So one can define an infinite hierarchy of undecidable problems. All right. Just to recap, in today's lecture, so we started out by seeing the implication of Turing reducing A to B. We showed that, if B is decidable, then A is decidable, and also saw the implication when taken contrapositively. Next, we did see a counterexample for the theorem not to hold for the recognizability. And finally, we said that, how powerful are Oracle Turing machines? Can there exist an Oracle which is powerful enough that, you can decide any language? And then we saw specific examples of constructing Oracle languages which are undecidable by Oracle Turing machines, which has access to halt TM. And then we said that we can generalize, in this fashion to build an infinite hierarchy of undecidable problems in this fashion, and hence there's no all-powerful Oracle which can access to which can, decide all languages. All right, thanks.